This is the first in a series of technical webinars that we will be hosting in the next few weeks. My name is Tommy. I am the business developer for the power switching and monitoring line of business for the Southeast Asia region. This webinar will last about 40 minutes or so. And at the end of the seminar, we will provide some contact details for you to get in touch with us should you have any questions. And we will also try to host a short 5 minutes FAQ towards the end of the webinar. So this recording will be made available to you after the webinar is completed. So now let us start. I would like to first do a quick introduction of who we are. Socomec is a specialist in the safety, control, availability, continuity, quality, and efficiency of low voltage installations. We are a French-based multinational corporation, and we have been in existence for the past 98 years. There are 5 main expertise within Socomec: power switching, power monitoring, power conversion, expert services, and energy storage. We have a worldwide presence, and for the APAC region, Singapore has been our headquarters for the past 36 years. Okay, so we'll start the webinar by going through first the agenda for today. So the purpose of this webinar is to introduce the isolated power supply, commonly termed as IPS, specifically in the application of hospitals and healthcare segment. We are planning to do this in 3 main parts. First, we will do an introduction to the electrical installation standard for medical location, which is the IEC 60364-7-710. Secondly, we will see how we can ensure the patient safety by exploring the various design considerations for the IPS panel. And finally, we will introduce the Socomec IPS solution that we call medsys, and we will highlight its main advantages. Okay, so IEC 60364-7-710 is an international standard which is dedicated to medical locations where it is necessary to ensure the safety of patients subjected to the application of medical equipment which are powered by electricity. Some countries have their own local standard with their own specific requirements, but more often than not, it is always based around the IEC. For example, the SS638 in Singapore, right, is contained within its Annex A is the specific requirements for medical installations, and it's largely based on IEC 60364. Countries like Thailand, Malaysia, Indonesia, for example, have also adopted the IEC for medical installation standards. So now if we were to go into the details of the standard, it is mentioned that the use of medical electrical equipment on patients undergoing intensive care has called for improved reliability and safety of electrical installations in hospitals so as to improve the safety and continuity of the power supply. For a better understanding of the medical installation, we need to focus on certain definitions. These definitions will give us a better overview of the main requirements for the medical location and therefore set the context for us to provide the solution with our medsys offer. Okay, the first important terminology in the IEC standard is what is known as the applied part. The applied part is the part of the medical electrical equipment which, in normal use, necessarily comes into physical contact with the patient for the equipment to perform its function, or can be brought into contact with the patient, or needs to be touched by the patient. So in this picture here, on the baby, the sensor is the applied part. The second important terminology in the IEC standard is what is called the group. The definition of group is related to the applied part. So as we can see here, the highest level of the group here is the medical location of group 2, where the applied parts are intended to be used in applications such as operating theaters and vital treatment, where discontinuity of the power supply can cause danger to life. The intermediate level of medical location is group 1, where applied parts are intended to be used externally, invasively to any part of the body except when group 2 applies. An example here would be the MRI scanning. And finally, group 0, where there are no applied parts to be used, therefore constituting the lowest risk. An example would be a physiotherapy room. So to summarize, the group is associated to the protection of patients against the possibility of an electrical shock. The third important terminology in the IEC standard is what is called class. The definition of class is related to the power availability and the authorized maximum duration of a power interruption. So for group 2, in the event of a voltage failure at the distribution board, a safety power supply, usually powered through a UPS, is required to maintain the lighting of the operating theater or the operation of key equipment. It shall restore the supply within a changeover period, not exceeding a certain period of time, which corresponds to the number coming after the term class. So therefore, class 0 means 0 second, and in which case that can be zero. It means that it must be zero blackout, right? No break of supply. Class 0.5 means 0.5 seconds of maximum power interruption. Class 15 or above 15 means 15 seconds or more of power interruption. So to sum up, the class is the way to define the level of service continuity. And we will see in the next few slides how to achieve these requirements and which product and solution has to be used. So here we can see a matrix indicating the availability classes and their mapping to the groups of medical location. We can see that the most critical applications like operating theater, intensive care unit, etc., falls under the group 2 category. So by looking at this mapping, it tells us that the group 2 category of medical location will require availability classes of less than 0.5. In some countries, the local standards will make it compulsory for class 0 at group 2. So do check and verify with your local regulations. In the next few slides, we will see how we can enhance the safety of patients in group 2 using different approach to the IPS design and configuration. Okay, so two main aspects we need to focus on in order to ensure safety of patients. The first is safety and protection against electrical shock. And secondly, it is the continuity of the power supply. In the critical medical locations, there are several risks that needs to be mitigated. And these risks can be due to the heart muscle being highly sensitive to electric currents, or the insertion of catheters into the body may reduce the electrical resistance of our skin. Body functions are temporarily or continuously substituted by medical electrical devices. Ventilators would be a good example nowadays. And also fire and explosion risks through the use of anesthetics, disinfectants, or cleaning solutions. Many of these risks are the consequences of an insulation fault. So therefore, we need to ensure the risk of an insulation fault is removed in the context of these critical locations. So in fact, insulation faults are created by impedance drops between one or more live conductors and exposed conductive parts. These abnormalities can occur when the installation is subjected to mechanical hazards and/or environmental hazards, for example, humidity or corrosion. They generate the circulation of abnormal currents and the presence of voltages, making the installation potentially dangerous. In addition to electrical safety, power availability will also be affected. So what are the effects of insulation faults? Stray currents, magnetic and electro corrosion effects, transient overvoltages and overcurrents, and all these can lead to malfunction, degradation, or danger when you come into contact with equipment. So the consequence is the impact on availability of supply and the safety of people and assets. The electrical installation must therefore be protected against insulation faults by installing, measuring, monitoring, and protection devices on the electrical network. Thus, IEC 60364 installation standard deals with insulation faults through a series of actions for preventing, locating, and eliminating these faults. And these actions are made possible by implementing earthing system with a suitable protection. So before we go deeply into the IT and earthing system, very quickly, we would like to remind everyone there are three types of earthing system that are permitted by IEC 60364. So these are the TT earthing, TN earthing, and IT systems. So IT systems, unlike the other two systems, the neutral of the source is not earthed. So therefore, the IT system is used in installations where operating continuity is essential, like in the case of medical locations. In the instance of a first insulation fault, the current will try to flow from the source to earth via the contact made on the equipment. However, because the IT source is not connected to the ground, the impedance that this fault current is subjected to is extremely high. So therefore, the intensity of this fault current is very low. The touch voltage will be less than 50 volts, which is safe for human contact. This allows the medical staff to continue with the operation and ensure continuity. The important point is that the faulty circuit must be identified and isolated to avoid a second failure, to avoid a second fault. And if a second fault were to occur, the fault current will complete its path back to the source. When this happens, the overcurrent protection will operate and there will be no more power to the affected equipment. Therefore, it is extremely important to act on the first fault. The use of an insulation monitoring device, or IMD for short, is mandatory to locate the occurrence of the first insulation fault. The IMD is also required to initiate an audible and visual alarm. So, in the case of Group 2 medical locations, an IT earthing system is created through an isolating transformer designed for medical use. It is used to feed power to all the appliances within the patient environment. And but generally, from the primary side, we are still on a TN network. So this transformer, this isolating transformer, has to ensure the separation between upstream and downstream circuits and to feed the loads in the operating room. It shall be installed in close proximity to the medical location, placed in cabinets or enclosures to prevent unintentional contact with live parts. And it has to comply with IEC 61558-2-15 and should not exceed 10 kVA in terms of rating. An IMD that complies to IEC 61557-8 is also mandatory to monitor and detect any fault. A remote alarm annunciator shall be arranged at a suitable location so that it can be permanently monitored by the medical staff and or maintenance staff, and this is also defined in the IEC 60364. So how else does an IT system ensure continuity? The electrical standard for medical locations states that in the main feeder of the IT system transformer, overcurrent protective devices are only used for protection against short circuits, so that an overload does not lead to a power failure. In the meantime, to have an idea of overload without tripping and ensuring continuity, monitoring of the transformer temperature and current is mandatory. In the case of an overload or overheating, signal alarms are sent to the remote annunciator, and shutdown actions can be done on unnecessary equipment to bring the load down. Now, let's discuss the various types of IPS architecture that can be commonly seen in hospital designs. So this is the first one, which is the most basic, with only the IT transformer and IMD monitoring the insulation. This architecture offers the least level of protection in terms of redundancy, as it is entirely dependent on the upstream source. So if the source upstream is interrupted in any way, the IPS loses its power. So to illustrate my point, right? So this is a single point of supply. So in this architecture, the IPS is not dependent on a single source. In the event the normal source, right, source A here, is down, the IPS will switch to an alternative source B, right? Therefore, ensuring the continuity of the operation. In this architecture, the IPS is rated class 0.5 as the switching is achieved by a break before make ATS. So if you can recall in the earlier slides, class 0.5 means a short break of 0.5 seconds. In this architecture, it is similar to the example before. The IPS is not dependent on a single source. However, the key difference here is that the redundancy is provided by two UPS sources. All right. UPS 1 and UPS 2. The IPS utilizes a static transfer switch to provide the switching function in the event UPS 1 is lost. All right. So if UPS 1 source is gone, you switch over to UPS 2. So this IPS architecture complies to class 0 thanks to the no break characteristics of the static transfer switch. In this architecture, which is similar to the solution with the ATS, but in this case, the backup power is achieved by the UPS, which is embedded inside the IPS panel. So therefore, effectively achieving class 0 compliance, as well as N redundancy on the upstream. So other than upstream power source redundancy, the load side has to have mitigation measures as well to ensure the safety of patients and availability of equipment. As said in the previous slides, the insulation fault has to be located and removed at the first instance. Otherwise, the occurrence of a second fault would trip protection devices and stop the continuity of service. In an intensive care unit, for example, sometimes up to 18 power sockets are supplying power to critical equipment. So for a 4-bed ICU unit, there could be more than 70 socket outlets. So usually there are no technicians present, or at least not immediately, and only the medical staff will be on hand. So if a defective device causes an fault, we need to ensure that the circuit or equipment associated to the fault can be easily identified, even by non-technical personnel. In order to guarantee the patient's safety, the insulation fault must be found as quickly as possible, and the solution to this is a fault locator. So now we have seen the two main aspects required in the standards dedicated to medical locations: the safety of the power supply as well as the continuity of the power supply. We have looked at the various types of IPS configuration or architecture to achieve these requirements. In addition, a very important point to keep in mind is that the IPS is an electrical equipment that is categorized as an LV assembly. And for LV assemblies, there are IEC compliances to ensure proper design and operation. Therefore, in a mission-critical application, such as the medical location, IEC 61439 for the IPS panel should be adhered. So what is behind the IEC 61439? It means that the LV assembly has been designed, qualified, and tested by respecting the 13 points inside the standard. The main criteria, for example, are short circuit withstand, IP protection, and withstanding temperature rise. And the temperature rise tests for IPS is particularly important due to the integration of the isolating transformer inside the cabinet. So that was the last slide on how we can enhance the safety of the hospital operation using the right IPS solution. To summarize, number one, the safety of people and assets. IT system achieves an optimum level of safety by greatly limiting the earth fault current level in case of insulation fault and direct contact with live parts. The fault current generated during a first failure is very low and thus do not have any damaging effect on the equipment. This helps to eliminate the high costs and delays due to possible repairs. Point number two, low risk of fire and explosion. Since the fault current remains very low, there is little risk of fire or explosion caused by a lack of insulation. Thanks to the monitoring of the transformer, this risk is highly reduced. Number three, the availability of electrical distribution is critical. So therefore, the IT system avoids switching off the supply circuit when the first insulation fault occurs, allowing to have a maximum level of availability. Coupling this with the right transfer switching equipment on the upstream can help to enhance this power availability to the maximum. And point number four, predictive maintenance. An insulation monitoring device, or IMD, is mandatory in the IT system. The IMD tracks evolution of insulation resistance and monitors its possible degradation. It will be possible to intervene even before the occurrence of a first fault. And this, for the last point, socomec solution does this extremely well, which we will see in the last section of this webinar. So now we will present the socomec range dedicated to the medical location and adapted to all electrical architecture. It means that it can be installed in new hospitals or even for retrofitting existing projects. You will see that all the core components that we have seen previously, such as the insulation monitoring device, the earth fault locator, the toroid CTs, and the transfer switch equipment, as well as the UPS, are all designed, tested, and qualified by socomec. It is a complete solution by a single manufacturer. The range is scalable, flexible, and can be easily adapted to the needs in terms of power requirement. And this is what we call the medsys. So as we can see here, medsys starts from 20, going all the way up to version medsys 60. So each version is able to reply to a certain level of class. medsys 20, 30, and 30 CD are for class 0.5. And medsys 40, medsys 60 are for class 0. So next, I will play a video to introduce the range. Okay, so what we have just seen in the video, embedded as part of the medsys solution, is the socomec IMD and earth fault locator. So these components are part of the socomec range called iZone DigiWare. So this technology is unique in the market because it is a two-in-one system that allows you to combine measurements of electrical parameters and the location of insulation faults. So here is an insulation monitoring device, which is represented by the L60H. Let me just get my pen out. So this is the L60H. This is the IMD. All right, and next to it is the F60H, which is the earth fault locator. So the toroid CTs are connected to this. Okay, and everything is connected to the D55H, which is the remote, which acts as a display as well as a remote annunciator. So iZone DigiWare is a fully customizable and scalable system, and it allows users to anticipate changes such as the addition of measurement points or circuits. It also brings easy integration and configuration with its plug-and-play approach. Sensors are connected to the modules using RJ12 cables and are recognized by the system at once it is interfaced to it. And the modules are interconnected via RJ45 cable, so it's an entirely plug-and-play system. In all medsys IPS, iZone DigiWare is configured as a standard offer. So finally, a full insulation health check of electrical installations can be established using a technology that we developed called the Ohm scanner. So what is Ohm scanner technology? Basically, Ohm scanner allows the user to monitor the insulation resistance of every feeder or equipment in real time. So this allows us to anticipate any potential fault. In addition, simultaneous measurement of other electrical parameters, such as current, allows us to do a correlation to the source and make a correlation to the degradation of insulation over time. Several layers of pre-alarms can be configured to allow for maintenance to react before an actual fault can occur. So what Ohm scanner technology really does is that it enables the predictive maintenance, which in turn enables costs and time savings, and most importantly, saving lives. So next, I will play a video to illustrate more about the Ohm scanner technology. Okay, so that was a video showcasing the Ohm scanner technology. Just a point to highlight, the Ohm scanner technology is a world first developed by socomec. So to conclude about the medsys offer, medsys is a range of standardized IPS cabinet that we know, but we know that all projects are different. So it can be for a new hospital or retrofit project. So that's why with the socomec range, we can reply to both thanks to the optimized footprint. Taking into account, of course, the heat dissipation, and we can prove this with the IEC 61439 compliance. Downtime can be kept to a minimum due to the use of reliable components like ATS, STS, and UPS, along with their bypass functions, all designed and produced by socomec. So thanks to the iZone DigiWare technology, an earth fault can be detected in less than 6 seconds, which is the fastest in the market today. With ohm scanner technology, we are able to predict any deviation on the electrical network and perform the necessary predictive maintenance. And finally, the possibility to add measurements very intuitively contributes to the main goals of safety and power availability. So this is one of the last point, right? On top of the initial functional tests after installation of the IPS, compliance to IEC 60364 requires for the periodic functional verification and inspection of the IPS panel. So this is similar to how we would do periodic tests on gensets, for example. So this periodic verification of the IPS shall be carried out in accordance with the local or national regulation. And for these kind of services, socomec has a dedicated team of service personnel and partners that can support our customers for commissioning, training, and periodic inspection on site. So to conclude this webinar, we support our customers in their project from the design phase all the way to the maintenance of the equipment through the equipment's lifespan. So get in touch with your nearest socomec contact for more details on our medsys